Alright, we're going to be talking about radioactivity and how to calculate half-lives and the amount of material that goes through radioactive decay. And the basic equation we're going to use is that our mass of our undecayed sample, so that the part that remains still radioactive, equals our mass initially times 1/2 raised to the nth power, where n happens to be the number of half-lives. So to calculate n, we take the time and we divide it by our half-life, and that gives us how many half-lives we have during that amount of time. Now your book does something like this. It does m initial times 1 over n 2 to the nth power. Just realize that this is the same as this. I like this one up here because I can type 0.5 for 1/2 and raise it to a power rather than dealing with trying to get this whole thing in a denominator. Okay. So I tend to use this one up here. But either one should give you the same answer. So let's go through a problem where we can actually use that. I'm going to pull the information out as we read through it. We've got a t of 1/2 that we were told is 10.0 minutes. And we begin with this much, so that's our initial mass, 55.2 milligrams of our isotope. And it asks how much is left after 20 minutes. So we're asking for how much is still radioactive after a time of 20 minutes. So first of all, we need to figure out what n is, right? We've got time 1/2. So our n is, let me use a different color here so we can keep it straight what we're calculating. N equals our time, which is 20 minutes, divided by our half-life, which is 10 minutes. So we have 2 half-lives during this time period. Now our mass that is still radioactive, our mass final, is going to equal our initial mass, which is 55.2 milligrams, times 1/2 raised to the nth power, where n happens to be our 2. Now I do suggest you go through your calculator and type these in to make sure you're getting the correct one and making sure you're doing the power right here. But our answer should be 13.8 milligrams. Now let's go ahead, and they may not ask you a straightforward question like this. They may ask you for some other piece of information. So let's go through one of those types of problems so that you can see how those are done as well. Okay, don't worry about not seeing me. The important thing is you see the work on the board. So here we've got an isotope of iron and its half-life, so our T 1/2 is going to equal 44.5 days. And it asks for how many milligrams of this milligrams of sample. So this many milligrams is how much we started with, because that's how much the sample initially was. So our sample initial is 53.7 milligrams. And we're asked for how much is lost by decay. So we want the mass that is lost. That is the mass that is no longer radioactive. In this time period. So our time happens to be 222.5 days. So the first thing we need to do is figure out how much actually remains radioactive, because that we need to know in order to calculate how much is lost. So we're going to start off the same way we did with the previous problem. We need to figure out how many half-lives go by. So we take our time and we divide it by our half-life, and we will get a 5 half-lives passing in that time period. So now we're going to figure out how much is still radioactive by using our equation. It's mass initial, which is our 53.7 milligrams, times 1/2 raised to the power of n, which in this case is 5. So when we go ahead and plug that into our calculator, we should get 1.68 milligrams. So is that what it asked us for? Did it ask us for how much is still radioactive? No, it asked us for how much is lost, how much is no longer radioactive. So the mass that we started out with is going to be the mass of what is radioactive plus the mass of what is not radioactive, right? Because this has to be one of those two things in the end. So we can solve for the mass of what's not radioactive by just subtracting over the other thing. And it equals the mass initial minus our mass, which is still radioactive, which we call mass final. Okay, so we started off with 53.7 milligrams, and the amount that remains after decay is 1.68. That's how much is still radioactive. So we subtract those two, and we should get 52.0 milligrams, which are no longer radioactive. This is how much is lost. So be careful about what you're asked for. If you're asked for how much is still radioactive, you're just solving for M final. If you're asked for how much is lost or how much is no longer radioactive, then you have to add this additional step of subtracting it from the initial one. Now, there are two more problems in your slides, which I'd like you to work on your own, that are exactly like this one up here, where you plug it straight into the formulas. There's no tricks about it. You just put them directly into the formula. And I will give you the answers here, but do work them on your own to make sure that you're able to get the correct answer. So the first problem states that we have a half-life of 10. It begins with 67.1 milligrams, and it asks how many milligrams are left after 40 minutes. So when you plug that into the formulas, you should get 4.19 milligrams. The next problem is exactly the same thing. Let me cover this up so that we can focus in on just what we've got here. It asks for how much remains as well. It's got some different numbers, but it's basically plugging it directly into the formula. So the answer is 5.28 milligrams. So try that one. Make sure you're getting the correct answer. The one I want to go through next on this slide is one that uses a little bit of math that you may have forgotten. So I want to make sure that we all remember how to do this math so that we can answer these types of questions. So we've got some information here at the beginning that we don't particularly need, but it says that we've got this lead isotope and it decays by beta emission. Okay, great. And it says that we started off with 90, so I'm going to write that as mass initial. It equals 98.5 milligrams, and it went down to this mass. So our mass final is 12.3 milligrams. In time, which is 63.0 years. And it asks for what is the half-life. Okay. So here we're going to use that equation, but we have to now solve for the half-life. So our equation starts off as mass final equals mass initial to the 1/2 raised to the nth power. Well, our half-life is in that n part of the equation. So we need to solve for n first. So first of all, we've got to get the term that has n in it. Remember, it's raised to the power of n. So we can't just multiply and divide to get isolate n. But we can get the term that has the n in it alone on one side. So we're going to divide both sides by m initial, and we're going to get the fact that 1/2 to the nth power is going to equal our m final minus, or divided by m initial. Now, in order to solve for this, does anyone remember how you solve for something that's in an exponent? Well, the way we would do this is to take the log of both sides. So we have to take the log of not just this side, but the other side as well. So we end up with the log of 1/2 raised to the nth power equals the log of m final over m initial. Now, we've got a rule here on how to solve for that n, and this is where I wanted to go through this because we may have forgotten it. If you have the log of something to a power, that's the same thing as taking that power and multiplying it by the log. So n times the log of 1/2 is the same as log of 1/2 to the nth power. So now we can get n by itself on that side just by dividing both sides by the log of 1/2. So our n is going to equal the log of m final over m initial divided by the log of 1/2. Okay. This is just algebra. It's nothing to do with the chemistry, okay? So we can go ahead and plug those numbers in. We can get the log. MF is our 12.3 milligrams. Our M initial is our 98.5 milligrams. And we're going to divide by the log of 1/2. Keep in mind, this top number is going to be negative, the bottom number is going to be negative, so they cancel out. So we end up with the number of half-lives being 3. Okay, make sure you can plug that into your calculator and you get 3. Well, the number of half-lives is your time divided by time 1/2. So we can just solve this for the half-life, multiply that over there, divide that over there. We end up with t 1/2 equaling t divided by n. You can then plug in our numbers. Our t is 63.0 years. Our n is 3. So our t 1/2 will calculate out to be 21 years. So that is our half-life. Now, I wanted to go through this one in particular to make sure that you understood how to do a problem like this. You do have to know how to do the algebra part. Okay. There's another problem that you can use to make sure that you understand this really well, and that's our one down here at the bottom. And it asks for how long it takes to decay from this mass to this mass. So here we've got mass initial, here we've got mass final, and here we have t 1/2, and it's asking us for t. Okay, so you go through this exact same process, but over here for n, you're solving for t. So I want you to try that one on your own. T should come out to be 13.1 hours. Okay. So practice this type of a solution, and this time we're solving for t, and see if you can get that correct answer at the bottom. It's good practice to make sure that you have the algebra part of this under control. Remember, algebra is not chemistry, so they're two separate things. So there's only a little bit of chemistry when you're trying to figure this part out, but you do need the algebra to make it work. So give these a try, and hopefully you'll have success in getting the correct answers.